I believe the record is now on. Okay, so it's time to, I hope that you get the behavior. Now it's time to get into the calculation side of things. Now, this is what we need to predict, right? The critical buckling stress of member under compression. Please keep in mind that it should not reach Fy by any case. Okay, and to predict this, remember we after all the perspectives, the aspects that we have to consider, and all the test results, they now split the design curve into two zones. Okay, you need to check this limit first. And this limit is this one, 4.71 square root E over F. Now, what do you check against this? You check the slenderness ratio of your compression member. If the slenderness ratio is larger than this limit, if it's larger, you are going to have the elastic behavior. Remember, the elastic is good in one thing, because once you unload your structure, everything goes back to normal. But that means the load is small, and you don't want to have the small load carrying capacity, right? And when you check this and your KL over R or L over R is larger than this limit, your compression member is going to have the elastic behavior. If it is smaller, you are going to have the inelastic behavior. Now keep in mind that when you look at this, when K over R or the L over R gets larger, goes that way, this curve keeps coming down. And so your stress is getting less and less and less. In the meantime, if your L over R becomes less, moves to the left, the curve keeps going up. Okay. Now, when we are going to predict this based on the elastic buckling stress, see that? That's pi square E over L over R square. And please keep in mind, just look at the formula. Some guys will forget the square term and things like that. Some guys will forget this square, or, you know, it's very, very sad. And to make it even more so very sad is that generally, you know, all the, if it's closed book exam like before, all the formulas are provided in the exam. And if it's open book, you can just, you know, look at the formulas. Okay. Now, if it's elastic, the critical buckling stress is simply this formula multiplied by that constant, you see? So that means when your compression member is in the elastic region, it just basically this elastic buckling stress and then reduced by some number, about 12%. You see that? That is the reduction due to out of straightness. Just need yeah, we just need to be sure that, you know, if that's the case, or let's say it's not been manufactured very well, it's slightly crooked, or maybe your load is a bit off center, you know, just to be sure that we are still safe, we put the reduction factor multiplied with the elastic buckling stress. Now, when it becomes the inelastic, it's simply a function of this elastic buckling stress, but then it gets a little bit more complicated. So that's a formula. 0.658 to the power of Fy over Fe, and this whole thing becomes a factor and multiply with Fy. So it's just simple. Once you know your member, you check the slenderness ratio L over R. Remember that R is radius of gyration, not the radius of the fillet, right? If the L over R is greater than this limit, you go into the elastic behavior, and this is your prediction. Okay, if it's less, you go into the inelastic behavior, and this is your prediction. Simple as that. Okay, but keep in mind that now, if you are going to design the compression, remember I always mention that when you design something, it means that you begin everything from zero. Nothing ever exists before that. In tension members, you know the stress. It's either going to reach yield or it's going to rupture. So you only have one unknown, that is the area. Okay? But when it comes down to this, the area, of course, is still the unknown, but the F critical becomes a function of the R, the radius of gyration, which is a function of your cross-section as well. So now you have one equation, two unknowns. That is why I have created the design aid, the table that can help facilitate your design in the future. Otherwise, you're going to have to keep guessing. Okay. Now, this is what it says on the specification. If you are like a scholar, you want to read from the origin, this is how it says. Okay. Nominal compressive strength is the F critical multiplied by this. If this is that, and then blah, 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 it's just the same thing. Okay. Now, this is what perhaps you asked earlier, and I haven't mentioned. The support condition will also dictate the behavior of your compression member. Because you can see now that the first one is both pin. It's kind of small. Can I expand? Yeah, I can. You can see that this is pin. This is also pin, pin, and pin. So the column is the beautiful sine curve. And if you can recall the formula that you developed in the mechanics of materials class, it's based on one perfect design curve. So you can say that K for this case is equal to 1. Now, when you fix both like this, notice that it carries more load. When you fix the rotation here becomes 0. So the sine curve is just about this length. So the sine curve, you know, the same sine curve is only half of the length of the member. Okay. When you fix one and then pin one, the sine curve, the perfect sine curve, just about, say, 70% of the length. And when you fix only one side, and this one is free, notice that the sine curve, it becomes longer, because in order to come back to this original place, it's about like 2L. Okay, so the support condition dictates the sine curve that you are going to have. And as a result, we must take this into the account. It comes into the form of the K factor, which we call effective length factor. This will give you a clear indication that if it's a typical case, this one, oops, this one you see, pin, pin, it's a basic sine curve. And the K value becomes 1 because the length of the member is equal to the length of the sine curve. And this is the recommended design value because it's a basic, so it's equal. But now when you change the support condition, fix this one, for example, this is a fix, okay? The sine curve is only 50% of the length of the member. Say about that much. So the theoretical K value is K. You can say that changing the support into fixed will help reduce the length of your member. Okay. So what is counted is the length of the sine curve. So it is down to only 50%. But as you know, you asked before about the support condition, and as I have explained before, that to have the truly fixed support is kind of difficult. So one moment, please. All right, now we resume the record. So because of that, we generally do not create the real fixed support. So we don't use 0.5. It is recommended that we use 0.65 instead. Okay, so you don't use the theoretical values. You use the recommended design value. Okay. Now, when you look at another case where, okay, so one pin, one fix like that, I say a 0.7, you don't use 0.7, you use 0.8 because, you know, the fixed support. Now, another very important case is this one. This. This is a cantilever column, so to speak, right? Remember that I used to mention this in the design of the frame, that when you don't fix your say frame and then you fix the support like this instead. Can you recall that? When you have this and then I don't want to fix this, I'm going to free this. And when you, okay, I may want, I can do this. I can fix the support. I don't want to fix it on top because of my difficulty in construction, whatever. Your column becomes something like this. And notice that in this case, K theoretical is 2 because of the cantilever. So your sine curve takes twice the length to come close its loop to form a sine curve. And remember, this is fixed. We don't want to use real fixed. So the recommended value becomes 2.1, you see? So let's say basically, if your column is 4 meters long, you are designing the column that is actually longer than 8 meters. It's twice the length. And L is square, so 4 square and 8 square, this is like 2 times greater. It's 64 over 16, 4 times. Right? So let me again use this. And in the second part of this class, you will deal with this compression member in the frame. And you must account for the K values in the columns in the frame as well, which is going to be slightly, you know, more than what we have as a single column like this. Okay. Now, any question about this?
Can you name the example of the top joint is translation fixed? Translation
fixed, which one?
Yeah, can you name the example in the real world that the top end is translation fixed?
Rotation free and translation fixed. It's kind of difficult, but we can say that the sum part of your truss member is going to be like this. We can treat it like this. Okay, or let's say, yeah, you have to be sure that it doesn't move sideways. And generally, it's very hard if you consider the frame in the real world. That's why I was saying that when you design the frame, you must account for the K by, you know, taking some other things into the account in the chance to touch part. I don't want to go too much. I have the answer, but I'm afraid that it might confuse you a little bit, but let's say if your frame is like this, okay, and if you know it's going to move sideways, because if I push it like this guy is going to go, okay. If it goes like that, it means that this is not this case anymore. It's going to be some case, and this is not really, the picture is a mess. You cannot say this is neither hinged nor fixed because it moves. So you must take into the account the effects of the, the beams that form the joints, and the columns that form the joints. And that's another way to do it. But let's say to have this, we may consider this case as some kind of a compression members in the truss, which I have the slide at the end of this chapter, you will see. Okay, it's a very good question. Okay, does it help? Does the answer help?
Yes.
Okay, thank you. All right. So, let's move on then. This, as I mentioned, when we have the doubly symmetric section, it's gonna buckle, the member is going to buckle about its principal axis in the one that is weaker, or say it is more slender. So you must check both axes like this and see which axis will produce the minimum KL over R. Now we don't talk about L over R anymore. You see, we must always say with a K because we account for the support condition. Okay. Now, because this, I see if, okay. One thing that it's, you have to understand one thing. This L here is not the length of the column itself. This L here that we use, what we say from the beginning, is called the unbraced length. So you can now say that the nominal strength of your compression member depends on the strength of material that you use and depends on the slenderness ratio of your member, which is the ratio of unbraced length over the radius of gyration multiplied by K. Now let's say if I have one column long like that. That's the length of the column. But somehow, let's say, I prevent the movement by adding some member in here, which I can call bracing. Now, this column will not be able to move at this particular point where I add the bracing. Right? When it is going to dance, it's going to dance like this. Right? That means this is my unbraced length. That is my unbraced length. Now, because I put it to the side, so if I look at this column from this direction, if my eyes is in that direction, I will see this view, correct? With the bracing to the side. Are you with me? Let's say it's a pin. Are you with me? I look at this view I look into this direction. So you know what, I can do this. I'm just gonna redraw this on the new page. This is getting too much. Let's say you guys pay attention, pay good attention. If I add the bracing here, okay, to distinguish this, I will paint this side blue. Okay, so when I look at the front view, so to speak, my eyes are here. I will see this. With the bracing to the side. And now the painting is clearly visible from the front. You guys see this, right? Hello?
Yes, yes.
Good. So now when I apply compression, because of the presence of this bracing, this compression member is going to, it's going to dance like this. It cannot dance here because of the presence of the support. All right, so that becomes my unbraced length. That too. That's the unbraced length, not the length of the column, you see? But now, when I look in another direction, say from here, say my eyes at the back now, looking at another way around, I see the back of the column. Correct? I don't see the color blue anymore. And the bracing becomes just a dot on the opposite side because I look from the back, right? Are you with me?
Yes, yes.
Good. So that means in this axis, your column is free to buckle with the entire length this time because there is no help. Correct?
Yes, yes.
Yeah. So when you consider, you must consider both axes. Now this axis has help. So when it is going to buckle, the unbraced length becomes the length between the support. I should add, I'm trying to make this as clear as possible. This is the brace. Okay. But when we consider this in another axis, you can say when it's going to buckle around this axis, it can just go with the entire length because it has no restraint to help stop its displacement. So the unbraced length becomes the entire length this time. I should be, let's say this is in the drawing, you're going to see that this is say 1-1, right? This is a view 1-1. Okay, and that is view number 2. So this becomes it's too close. Hang on. That's better. This is your view 2-2. Okay. So now we must, for a doubly symmetric section, we must consider both axes. Now, what is bracing? Bracing is something that can stop the lateral displacement of your compression member. So anything that you put in there, that it will prevent the lateral movement at the particular point is your bracing. And it will reduce the unbraced length of your member. Now, you must remember that the strength of your compression member is a function of the unbraced length, is not the function of the length of the entire member. So that means even if I have a column 30 meters long, but I can brace them, say, every 3 meters, the load carrying capacity would depend on 3 meters, not 30. Okay? Question, please. Must understand this first.
In case, okay, I have a question.
Please, please, please.
If the brace as you draw here is we change to lower than a little bit, that means the unbraced length will have 2 parts. Which one is longer, which one is shorter, right?
That's correct.
Yeah, and in this case, which number we're gonna use, or it depends on the situation?
Well, you know what? Your question is very good. You have a good observation. I wonder why you cannot answer that yourself. Let me draw this for you. Let's say we have your case. And I'm going to draw it so that it's very clearly visible that, you know, unbraced length are not equal, like that. That's serve you right, PIs?
Yes.
Okay.
Yes.
So now, let me ask you further. This one clearly is longer, right?
Yes.
Draw the support as well. This one is shorter. If I apply compression, which part is going to go first? L1 or L2?
I think L1.
Yes, so L1 is going to go first. So that is your answer.
Oh, okay, I see.
Right?
L-way, the thing that is the longer part all the time, right?
You should say properly the part with larger slenderness ratio.
Oh, okay, because it's
Longer doesn't necessarily mean it's slender, it's more slender, right?
Yes. Okay.
Good. So yeah.
In the other hand, if we change the brace in the upper one, that means the length will become the lower part with the longer, right? The bracing length. If we change bracing to upper part.
What do you mean? If I move this up,
okay. Line up, yeah.
If I move it like this,
Up, yeah. Upper.
This is where the lateral movement is prevented.
Oh.
That's the point of the bracing. You prevent lateral movement.
Oh, okay.
Anything that prevent lateral movement, it becomes a brace point of your structure.
Okay.
Crystal clear?
Yeah, clear. Thank you very much.
Now the point is this. Sometimes you cannot brace in the middle. We don't know the conditions of architecture. Sometimes the point of bracing is available to you at some point. You would want to use it if you could. And it may look absurd if everything is on paper. You can do what you want. Why brace so that L1 is longer than L2, right? Seems unwise, but because you never know what conditions you're gonna have. So you may end up something like this, and then you know, because this this part is more slender, so it's gonna buckle first, right? That's what it is. Understand the behavior, talk to the structure. Okay. Anapat, go ahead.
Can you move to the upper page?
Okay.
Yeah. I wonder if we have an ideal pin on the top. May I draw on your screen?
I don't know
if
how.
we have if we have an ideal pin on in this direction, so it means that it can rotate in this way. But if we consider in the view 2.2, we have another side of the pin, so that it cannot rotate in this way.
If you give the symbol like that, it means that you should make your structure rotate.
Rotate in
let's say let's say because to have the pin in the real world can be difficult, but yes, it depends on the condition of your structure. You must consider both axes and see if both directions are pinned. Only that you can write pin on both views like this. You ask me if it's possible that maybe we can have a pin in one direction and fix it in another. Yes, it is possible. Maybe, I say. And we can go back and discuss on this, because when you are going to have the class in a frame like this, you know, frame in one axis may not have the same K as frame in, say, out of plane axis. So if I'm going to draw this picture again in 3D, okay. All right, this one. Let's say we're going to have the building here. That one, that lies. Okay. Let's say we are going to consider this. Okay. All right. Let's say we are going to try to consider this compression member. So now you see the K or the behavior of this column in this direction, in plane, okay, in this plane, will be dictated by these two beams coming in, right? So when we consider the K in this direction, it's going to be dictated by this, perhaps, and then actually it should be, yeah, it depends on the type of the frame that this is in. And then in this direction, that's another thing. You should consider this frame as something else. And let's say, because K is a sigma I over L, so it may come out to be the same, it may not. But remember that the radius of gyration of both directions of this column will not be the same if you use, to say, an H. Okay. So this, when you consider this, you may not have the same K in both directions. When you consider buckling of the in-plane blue one here, or the out of plane, which is in this direction. All right. So yes, you may have the same K in both axes. You may have different K. So you must consider both axes. You should pick up more details with the Jan Sutat in this regard. Okay. That is a difficult question, and then so the answer comes out sounds a bit difficult as well. Is there any question? Any more question about this? And yes, we're gonna have the example of the thrust in the end, and we need to consider both axes, and K will be different as well. All right, that will suit you. Okay. Any more on this, please? I truly welcome questions, and it's a joy to discuss with you guys. Much better than speaking alone. Okay, and it opens up the world for you. So keep them coming. Okay, all the questions are good. Any more? Oh, not for now. Remember, it's a function of unbraced length, not the length of the member. Okay, so we move on here. You must check both axes and K in both directions. All right. Now, next thing. Before we go into local buckling, let me spend a minute or two here telling you guys this. It's a problem with the angle. Now, I believe that many of you will go out and design angles in the real world. The problem with the angle, I probably have mentioned before, that is this. By nature, this is the angle. Okay? By nature, the centroid of the angle is in the air. In the air. And the principal axis is not XY. First, centroid in the air. Second, principal axis is not XY axis. Is this Z axis? So to account for this kind of problem, they now suggest that you calculate the unbraced length and modify it before you use that formula. Remember, we have one formula, which is this one. No matter what we do, this is the formula that you have. Okay? You check your slenderness ratio with this limiting value. If your slenderness ratio KL over R now, not L over R, if your slenderness ratio exceeds this value, you have the elastic behavior, and you predict the strength by using this formula, which is a function of Fe. If your slenderness ratio is less than this limiting value, you predict your strength in the inelastic region by using this formula, which is also a function of Fe. That's it. So now, when you can do self-study in the future, and when you look at the angle and you have that case, you need to modify your L over R further before you do all this. That's all. Okay. It's just the say sideways knowledge. I'm not going to give the problems with the angle. I think it's probably too advanced in a way. But the funny thing is that people, engineers, use angle a lot in the real world, and they have the old ways of design, which is not bad. Instead of using the principal axis, you need to use R in the principal axis, which is not bad. You can also do that. But nowadays they have the new approach that requires you to modify the KL over R. Once you modify it, you can use the formula, and that's it. Okay, no more of this. All right. So now The next thing you need to know is the local buckling. Now remember, let's say for example, we are going to use the Y flange or the edge shape a lot. If one of your elements become too slender, the local buckling may occur in the particular element before your member buckles. Okay? Some local failure around here may occur before your member fails due to stability issue. So that will prevent your member to even reach the F critical. So you say, I can summarize here that compression, buckling will prevent you from reaching Fy. And then local buckling prevents what? Prevents the reaching of F critical. So it's getting even lower. Okay. Now, in considering the local buckling issue, the AISC categorize the elements into two types. The first is called unstiffened element. The second is stiffened element. The key is the definition can be slightly confusing, but it's not a big deal at all. Unstiffened element is the compression element with adjoining out of plane element along one edge parallel to the direction of loading. So let's say this is a compression member. The direction of loading is this. The direction parallel to loading, therefore, is something. It's this direction, correct? And it says here, with an adjoining along one edge. So you see this flange, this particular flange, has one edge, that one edge. So, and I can say that, I can draw it again, say, yeah, now the flange look like this. That is a free end, and that becomes the adjoining out of plane element, whatever that is, in the pink line here. So the flange itself has one support. So it is therefore an unstiffened element. Now we move on to the stiffened element. Say you have the flat compression element with adjoining outer plane elements along both edges. So let's look at the web now. You see, when you look at the web, this becomes the one adjoining plane, and this is another, right? So you can see that now the web has two supports, so to speak. So the web is therefore the stiffened element. Okay, so now the reason we need to categorize this is that because it has its own different limiting values. Okay, and we are going to, of course, consider the slenderness ratio of this as well. So this becomes the B, and that is the thickness. So the slenderness ratio is B over T. And likewise here, B and T, we consider the B over T ratio here and compare it with the limiting value. All right. If this ratio does not exceed the limiting value lambda r, the local buckling should not occur, will not occur before lateral buckling. If your ratio is smaller than lambda r, the limiting value, the local buckling may occur before the lateral buckling. Therefore, instead of making your member unable to reach F critical, because this sum like this will occur before your member actually goes sideways. Okay? Question? Is there any question? Is there any question? Is there any question? Perhaps not. Pretty straightforward. And okay, if there isn't, let me finish this here. There is this table available. You can also look at from the handout that I give you. Say here, this is the case of the unstiffened element. See, it flange or rotate. Now it's flange because it has one support here, so it becomes unstiffened element. You check this with this very universal limiting ratio 0.56 square root E over Fy. Okay. Now, if it is the leg of the angle like this, or the crucifix, the limit becomes 0.45 because the angle is just like two unstiffened elements put together. So it's not as strong as the flange, which is connected to the web. So the limit is lower. Okay. Now we have stiffened element, which is the web. Now, you see, because it's a stiffened element, so the limiting value becomes considerably larger. See, 0.56 with 1.49, that's like 3 times greater. So that suggests that your web should be much harder to buckle locally, which is correct. And then you have another value when you consider the rectangular or the box like this, it becomes 1.4 instead of 1.49. So be careful. And when you use the circular section like this, the limit becomes entirely different. And because this is stiffened element, right? It just, wow, where's the support? It's round. So it's entirely different limiting value. And you see, there's no square root in it. It's 0.11 E over Fy. Okay, so that's 11:20 already. So let me stop here and I'll come back here for more information on this. Unless, of course, you have a question. Any question? If not, let's